take the function psi sub k of x equal sine of kx, and the operator a indicating the second derivative, d squared over dx squared. Applying this operator to the function, we get d squared ddx squared of sine kx equals, and now we apply the first derivative first, minus ddx of minus k times cosine kx, which is equal to minus k squared times sine kx. Even though we operated on the function with a second derivative, which is usually a pretty massive operation, the function did not change. It was sine kx before, and it is sine kx after the application of the operator. The only change is that it has now a constant as a prefactor. This wouldn't have worked with most other functions. For example, x cubed in here would have given 6x as a result. More generally, we can write a operating on psi k of x equals ak times psi k of x. A is the operator. Psi k is the function that is unaffected by the operator to within a multiplicative constant. Such a function is called an eigenfunction of the operator. For example, here, psi is an eigenfunction of the operator a. Lowercase a sub k is called the eigenvalue associated with that eigenfunction. Eigenfunctions and eigenvalues come in pairs. The overall equation is called an eigenvalue equation. In our initial example, k can have any value. Therefore, there is an infinite amount of eigenfunctions in our example, each with its own associated eigenvalue. This is in general true for operators and used in quantum theory. Eigenvalues and eigenfunctions are central in quantum theory. First of all, the time-independent Schrödinger equation is an eigenvalue equation. H operating on psi equals E times psi. The operator in a Schrödinger equation is the Hamiltonian, which is the operator representing the total energy. The solution of this eigenvalue equation consists of a set of energy eigenfunctions with associated energy eigenvalues. Secondly, other measurable quantities are associated with operators as well. Such measurable quantities are called observables. They also have associated eigenfunctions and eigenvalues, and eigenvalue equations. For example, the eigenvalue equation for the momentum operator is h bar over I ddx. This is the momentum operator, operating on phi of x equals p times phi of x, where p represents a momentum eigenvalue. Thirdly, one of the basic postulates of quantum theory is that if you measure property A, represented by an operator A hat, you can only get one of the eigenvalues of the operator as a result. For example, when measuring the total energy of a system, you can only get eigenvalues of the total energy operator, which is the Hamiltonian operator.